Molecular dynamics operates on a strict mechanical premise. We can understand a complex system by calculating the forces on its atoms and propagating their coordinates forward in time using classical physics. The ultimate goal is to use these atomic trajectories to predict macroscopic thermodynamic properties, metrics like binding affinity, heat capacity, and free energy. But experimental measurements operate on an entirely different scale. An in vitro reading of a lipid vesicle simultaneously averages the states of a mole of molecules, roughly 10 to the 23rd power, in a single instant. A molecular dynamic simulation, conversely, is spatially bounded. It tracks a microscopic fraction of a single system, capturing interactions within a narrowly defined geometric box. It is also temporally bounded. The computational cost of integrating complex equations of motion limits most standard simulations to the nanosecond or microsecond timescale. Extrapolating a microsecond simulation of a few thousand atoms to represent a macroscopic reality requires a specific mathematical bridge. We rely on a foundational axiom of statistical mechanics, the ergodic hypothesis. To define ergodicity, we construct this coordinate grid. It represents phase space, denoted as gamma. It maps every possible position, q, and momentum, p, of every particle in a system. A single point here represents the exact state of an entire system at a specific moment. A physical system has 3n degrees of freedom, where n is the number of particles. This means true phase space is unfathomably vast, extending into millions of dimensions. Within this expanse, the system distributes itself according to a probability density, ρ. This acts as a topography of probability, dictating exactly how likely the system is to exist in any specific microstate based on its thermodynamic conditions. The exact thermodynamic property of a system, what we actually measure in a lab, is the ensemble average. This equation is the strict mathematical integral of an observable across all possible microstates, weighted precisely by their probability. A computer simulation cannot calculate this infinite spatial integral. Instead, molecular dynamics computes a time average. It calculates the motion of a single deterministic trajectory as it travels through phase space over time. The ergodic hypothesis states that if a system is allowed to evolve for infinite time, a single continuous trajectory will eventually visit every accessible microstate, doing so in exact proportion to its equilibrium probability. Because of this rule, the infinite time average and the ensemble average are mathematically identical. This equivalency gives molecular dynamics the theoretical authority to predict physical reality. While ergodicity holds true mathematically as time approaches infinity, it collapses under the strict constraints of finite computational time. Complex biomolecules exist on incredibly rugged energy landscapes. These topological profiles are characterized by deep, localized energy wells, metastable states, separated by massive free energy barriers. Even when energy barriers are low, systems face entropy bottlenecks. These are geometric pathways in phase space so narrow that a randomly wandering trajectory is statistically unlikely to ever discover them. Navigating these bottlenecks or climbing massive barriers are rare events. Consequently, a standard microsecond trajectory experiences kinetic trapping. The system falls into a local minimum, lacking the thermal energy to escape. This state is known as quasi-non-ergodicity. A finite time measurement trapped in a single well generates an average entirely biased by its starting coordinates, failing to represent the true thermodynamic ensemble. A persistent misconception is that extending the duration of a single trapped simulation will eventually force it to reach equilibrium. The mathematics of rare events dictate otherwise. If the natural barrier crossing time is 100 microseconds, spending a computational budget to run a 10 microsecond trajectory yields exactly 0 transitions. Overcoming this limitation requires abandoning the single trajectory paradigm. The operational standard is to deploy multiple independent replicate trajectories. Crucially, these must be seeded from sequentially uncorrelated, distinct initial conformations. By distributing starting points across known metastable states, the simulation maps disparate regions simultaneously. Combining this data reconstructs the probability density far more accurately than one continuous run grinding endlessly in a single well. Replicate sampling also provides the necessary data to measure statistical variance between independent runs. Analyzing this variance yields a strict quantitative measure of uncertainty. It prevents the false confidence that arises when a highly correlated trajectory produces a smooth but entirely inaccurate average. If replicates from different starting states fail to converge on a unified value over time, the system is demonstrably non-ergodic on the simulation timescale. However, standard replicate sampling has a hard limitation. If the energy barriers are absolute, replicates will map the isolated wells perfectly, but never capture the thermodynamics of the transition path between them. When natural barrier crossing is statistically impossible, passive observation is insufficient. Researchers must actively manipulate the underlying Hamiltonian. This requirement drives the use of enhanced sampling methods, algorithmic strategies designed to artificially bypass kinetic bottlenecks. This diagram illustrates one of the primary architectural solutions, replica exchange molecular dynamics, or REMD. It runs parallel, non-interacting replicas of the same system simultaneously. These replicas are distributed across a temperature ladder. The higher temperatures inject the requisite kinetic energy into the system needed to overcome local barriers. Relative to the available thermal energy, the effective height of the energy barriers flattens significantly on the hotter landscapes. Periodically, the algorithm invokes the metropolis exchange criterion. It evaluates the energies of adjacent replicas and attempts to instantly swap their atomic coordinates across the temperature ladder. Crucially, this statistical swap is strictly controlled to preserve the exact Boltzmann weighting required to maintain physical validity. REMD engineers a mathematical shortcut through the landscape. It replaces an impossible sequential chronological weight with parallelized thermodynamics. We can trace the operational life cycle of a single set of coordinates. A trajectory becomes trapped in a deep well at the target temperature. It swaps up the ladder, uses the thermal energy of the hottest landscape to glide over the flattened barrier into a new state, and then swaps back down. These high-temperature excursions continuously discover previously inaccessible conformations and feed them back down to the target ensemble. True ergodicity is rarely an inherent property of a finite-time biomolecular simulation. It is a mathematical ideal that must be explicitly engineered. Modern molecular dynamics is a deliberate strategy of importance-weighted sampling. Achieving physical validity requires strict command over the simulation's statistical mechanics. It relies entirely on understanding the vastness of phase space, identifying the geometric realities of quasi-non-ergodicity, and architecting the specific algorithmic path to defeat it.